So we're going to talk about bond energy. Okay, bond energies are the energy required to break 1 mole of bonds. So here's some example of some bond energy. If I wanted to break a carbon-carbon bond, it would be 347 kilojoules per mole. A carbon-carbon double bond is 612. A carbon-carbon triple bond is 820. Notice that triple bonds are stronger than single bonds, right? But also note that a double bond is not twice as much as a single bond, and a triple bond is not 3 times as much as a single bond. Yep, and here's a couple others. And again, you'll get a table of all the bond energies in a packet of tables that I'm going to give you. Bond energies are kind of useful, but not really. They allow us to estimate the heat of reaction. So in a pinch, we really want to use heats of formation, but it is possible to use them, the bond energies, to estimate the heat of reaction. What you do is you add energy for all the bonds that you break, and you subtract energy for all the bonds you form. So this means you need Lewis structures. So for instance, I do this out, and that's hydrogen, okay, that's chlorine. I need Lewis structures so I know if I have single or double bonds, and here I have 2 of these. So for all of the reactants, okay, I'm going to go ahead and add. You got to look up the bond energies in the table. This one's 436 plus a chlorine-chlorine bond is 243, and minus this one here is 2 times 431. So if you do all that out, you get minus 183 kilojoules. Okay. Now this reaction is just a heat of formation, right? The heat of formation for HCl, if you were to look it up, is minus 92.3. And since there's 2 of them, if we double that, we get minus 184.6. Okay, that would be the value we got if we used heats of formation. Pretty close to what we get with bond energies, because reactions really are more complicated than just breaking and reforming bonds. But you may be asked to do this, so this is how you do it. Just to give you an idea, as reactions get more complicated, okay, so we're going to have to draw out this Lewis structure, okay, otherwise we won't know how many bonds we're breaking. So this takes a lot longer than heats of formation as well. That's that one. Oxygen, remember oxygen's a single bond. This is a double bond. And this is a single bonds. Okay, so if we look, we see that we have 1, 2, 3, 4, 5 carbon-hydrogen bonds. Okay, we have a carbon-carbon bond. We have a carbon-oxygen bond. And we have an oxygen-hydrogen bond. Okay, and we also have 3 OO bonds. And then we're going to subtract over there. I've got 1, 2 times 2 is 4 C double bond O bonds. And 3 times 2, so we're subtracting these now, so minus 6 times OH. So you can see that you've got all these bonds, and so you fill in your numbers and you get your value. And if you were to do this, and we won't bother because it's really not that exciting, you would see that this value is not all that close to the value we get for the heats of formation. So it's an estimate, and sometimes as reactions get more complicated, it's not even a very good estimate. So whenever you have a choice, you're going to use heats of formation. You would only use bond energies if they said you had to.